In this video we will be implementing the forward pass, which is the mechanism by which a neural network receives some input on the left and then produces some output. So if I open the drawing I have, what I mean is, in the forward pass is when we give these things to the network and then the network propagates them from one layer to the other until something comes out over here. And as we have seen in a previous video, the way this is done is by means of matrix multiplication with the weight matrix, and then summing the bias vector, and then using the activation function. So although the weight matrices and the bias vectors change, this is always the same structure. This is always the same algorithm. And so we will have an auxiliary function that performs this step of multiplying by weight matrix and summing bias vector and applying activation function, and we will use the power operator to perform repeated application of that function. Also, I think it's important to note that as we implement this, I'm foreseeing that I will make some mistakes, so we will probably have to debug this together. But, well, let's do it. So the first thing to note is that the forward pass will take the activation function as a operand, so that you can later create your own activation functions and use them in your machine learning framework. So as this will be an operator, let's use the underscore to represent that. Let's call this the forward pass, and let's establish what goes where. So alpha is going to be the activation function. We call it alpha is the left operand, and then let's say that alpha, the left argument, is the network itself, and omega is the network input. So the first thing we are going to do is to unpack the network into the weight matrices and the bias vectors. So that's alpha, and also, yeah, that's it. The network input is W. It's omega. Okay. Now the next step is to perform repeated application of some auxiliary operand we're going to have that performs the step I mentioned of multiplying the matrices and summing the bias vectors and applying the activation function. So this auxiliary function, which is actually an operator, will also need the activation function. So we need to give it. We need to make sure that the activation function goes into the auxiliary operator. And then how many times do we need to apply this algorithm of multiplying by some weight matrix and summing some bias vector? Well, if you let me change into the sketch, you can see here that you need to make this as many times as there are gaps in the layers. So 1, 2 times. This is exactly the same number of weight matrices you have. So we can go right ahead and tally the number of matrices, weight matrices we have, and then apply this function that many times. Now we just have to give our auxiliary operator the necessary arguments. And what the operator needs is clearly a list of the weight matrices and a list of the bias vectors, but also the input the network got, so that it can propagate the input forward. But there's something else that I haven't told you yet, and that is, we will see that it's very useful to store intermediate results as well. So what I mean is, if I open the sketch again, as we perform these multiplications and additions, it is very useful if we store all the intermediate values that we get for later. And so we will be doing that. We will be accumulating these intermediate results, and then the network output will be the last one. So in this case, we would have an intermediate result here, and the final result here. So in order to do that, let's give our function a list of weight matrices, and by a list I mean a vector of weight matrices, a vector of bias vectors, and now a vector of the intermediate results. But this is just a vector, and I want to create a vector whose elements are vectors themselves, so I'm going to go ahead and enclose this. And now let's say that at the other end this will return the exact same thing, except that the x's are the intermediate values, and then to be honest we don't care about whatever happens to these, so you can just ignore them, and then in the end we will be returning the x's. And the way I know that this is going to be a triplet, like the triplet that we are giving it here, is that this function is going to get applied repeatedly to this argument. So it's easier if the return value of this function has the same shape as the input, so that we can perform repeated application. So that is exactly what is going on. And also notice that I refer to this as an operator, but to this together as a function, because as soon as you give all the operands an operator needs, APL creates a function for you. So here is the forward pass. Now we need to define our auxiliary f function, and let's say that alpha is the activation function, and let's say that w's, b's, and x's from omega are the components of the for the calculations. Yeah, sure, are the components for the calculations. So the first thing we're going to do is to unpack everything. Oops. And then what we can do is perform one step to produce the next intermediate value, save it to the list of intermediate values, and drop the matrix and the bias vector we just used, so that the next step knows which matrix to use and which vector to use. So making it very explicit, let's say that the matrix we want to use is the first available one, and the bias vector is the first one, and the value that is the input for this specific layer is the last one that we calculated, because we are accumulating the values at the end of the list of x's, and so the next value is going to be the bias vector plus matrix multiplication of the input with the weight matrix. And after all of this we need to apply the activation function. So this is the x. Then what do we need to do? We need to return all the matrices except the first one, and we need to return all the bias vectors except the first one, and then we need to return the x's together with the value we just computed, except this is a vector of vectors and this is just a vector, so we need to enclose it. Now if I press escape to fix this and escape to fix this, let's go ahead and create a neural network. In its network, let's say it has the 362 shape of the example. Here is the function. And now let's use the bind operator to create an activation function that only needs one input, because the leaky ReLU expects a parameter. And now let's give this to the forward pass and give the network on the left like we decided, and now this should be the network input, and let's say it's the column vector 1, 0, 0. Let's see how many mistakes I have. Okay, great, not many. Okay, so this looks like it's working. I've implemented this a couple of times already, so thank God it worked at the first try. So let's go over this again just one more time so you're sure you understood. If you understood this perfectly, feel free to skip to the next video, otherwise I'll review everything. So let's start with the input to the network. this table 100 creates a column vector. This is going to be the input to the network, and this 100 is going to be fed to the network over here. This is what is coming in. We are using this as our activation function. I'm using the bind operator to carry the leaky parameter to the function so that we just need the vector. For example, if I have 0.01 leaky value and then apply it to -2, 3, actually 4, -2, 2, this is what happens. So notice that the negative numbers were multiplied by the leaky parameter. And then I'm also giving the network as an input to the forward pass. So let me go ahead and open the forward pass again. I'm missing the underscore there. Okay, and this is a very simple function, actually a very simple operator, as you can see. I'm just unpacking the contents of the network to split them into weight matrices and bias vectors, because as you recall, when you initialize a network over here, you are getting a list of matrices. So this is the first matrix, and then the second matrix here, and then the bias vectors. So I am unpacking everything. If I do it here, I can do, say, W's B's gets the net, and so W's is the matrices and B's is the bias vectors. So I unpack that, and then I give it to some magical function I was yet to define, like this. I'm giving it the list, and by list I mean, strictly speaking, the vector of weight matrices, the vector of bias column vectors, and then a scalar with the network inputs. And the point was, I want to accumulate these intermediate steps, so I want to be creating another vector of vectors, and the easiest way to do so is by ensuring I already have a vector at the start, except that of course this vector only has a single element. So if I go ahead and check what the enclose, remember that the input is table 100, so if I enclose that, I get the vector with a single element. So we do that here, and then we say, well, whatever happens in here, we are going to return more or less the same thing, at least with the same shape, so that it's easy to apply the function repeatedly, and then we just return the intermediate values, because that's what we care about. And then, well, how many times do we have to apply this, the forward pass thingy? Well, as many times as there are weight matrices or bias vectors. Either way would work. So we can replace this with B's, for example. And now we are just left with specifying what this does. So let me go ahead and save it with B so that we can see it works as well. Oops, I didn't mean to edit this. Okay, underscore F. And here is F. So recall that we gave it 3 things as the argument, so we unpack everything, and then we say that the first matrix we want to use is the one that is available first, and the bias vector as well. It's the bias vector relative to this layer over here, and so we unpack them. We extract them with the disclose primitive, and then we say that the intermediate value we want to use to produce the next one is the most recent one. So as we walk along here, as soon as there's some intermediate output right here, that is the output we want to use for this multiplication right here. We don't want to use the first one again. So we pick the most recent one by using the pick last idiom, and then we perform the matrix multiplication, we submit the bias vector, and then we apply the activation function. And after that is done, we make sure to augment our vector of intermediate results correctly, because if we remove this, we will be adding the separate elements of this vector to this vector over here. So this ensures that we are extending the vector as we want, and then we just drop the matrix we just used and the bias vector we just used. So let me go ahead and also save this, although I don't think I made any changes. And if I run this again, you'll see it still works, and because everything is fixed, so there's no random number generation, no random number generation going on, the result is always the same, obviously. You can try changing the input to see what happens, let's say a 1 over there, and the results are different. And so in the next videos, what we will be covering is how to take this network output, compare it to the output we were expecting, and then correct the network, that is, train the network to produce the values we want and expect.